Today we're going to talk about the solar system. The planets in our solar system vary greatly in terms of their distances from the sun, atmospheres, surface temperatures, and many other factors. Some of the solar system's planets have very thick, dense atmospheres, while others have thin, low-density atmospheres or virtually no atmosphere at all. Some planets have extremely high surface temperatures, while other planets have extremely cold surface temperatures. Some planets are relatively close to the sun and orbit it at a rapid rate. Other planets, on the other hand, move slowly and take thousands of Earth days to complete one full orbit around the sun. Each planet in the solar system has a unique orbit around the sun and a unique average distance from the sun. The diagram below shows the relative average distances of the planets from the sun. As you can see, Mercury, Venus, Earth, and Mars are very close to the sun in comparison to Jupiter, Saturn, Uranus, and Neptune. The planets that are closer to the sun tend to move at greater speeds and have shorter years. The table below shows the average orbital speed of each planet. Notice that the farther a planet is from the sun, the slower it moves. And since the planets farther from the sun have farther to travel to complete one orbit, they also have much longer years. A planet's distance from the sun is also one of the most important factors influencing its surface temperature. Well, that makes sense. The table below shows the surface temperature of each planet. In general, the farther away from the sun a planet is, the lower its surface temperature tends to be. However, there are some important exceptions. Venus, for example, has the highest surface temperature of all the planets, but it's actually farther from the sun than Mercury. The difference is due to the very different atmospheres of Venus and Mercury. The thickness of a planet's atmosphere is in part due to the strength of the planet's gravitational field. A very massive planet with a very strong gravitational field is likely to have a very thick atmosphere. Jupiter, Saturn, Uranus, and Neptune, for example, have strong gravitational fields and thick, dense atmospheres. Mercury, on the other hand, has a weak gravitational field and an extremely thin, low-density atmosphere. The particles in Mercury's atmosphere are so far apart that they are more likely to collide with the planet's surface than with each other. Here's a breakdown of the Mercurian atmosphere composition. It's made mainly of hydrogen, helium, a little bit of potassium, oxygen, and sodium. Venus has a very thick, dense, cloudy atmosphere that hides the planet's surface from view. The atmosphere of Venus is made mostly of carbon dioxide, with a lesser amount of nitrogen and trace amounts of other gases including sulfur dioxide, argon, and water vapor. The main source of Venus's atmospheric gases is volcanic eruptions that occurred earlier in its history, although impacting objects may have added some materials as well. Because of the high concentration of carbon dioxide, Venus has a runaway greenhouse effect that is much stronger than Earth's greenhouse effect. Because of its powerful greenhouse effect and its distance from the sun, Venus has a surface temperature of about 465 degrees Celsius, which is the highest of all the planets. Here is a picture of Venus's atmosphere. You can see the sulfuric acid cloud and haze layers. Although not as thick and dense as Venus's atmosphere, Earth's atmosphere is thicker and denser than the atmospheres of other rocky inner planets. Earth's atmosphere developed from volcanic eruptions, biological processes, and early impacts by comets and asteroids. Mars has a thin, low-density atmosphere. The atmospheric pressure on the surface of Mars is only about 1/150th of the atmospheric pressure on Earth's surface. Mars' atmosphere came mainly from past volcanic eruptions, with additional contributions likely from impacting bodies. Here's a breakdown of Mars' atmosphere. You can see in the troposphere we've got dust and then water and ice clouds. Up above that, as you increase in altitude, you've got carbon dioxide ice clouds. Past Mars, the planets of the solar system have very large and thick atmospheres. Jupiter, Saturn, Uranus, and Neptune are giant balls of gas and compressed liquids with very small, rocky, icy cores. Their atmospheres formed very early in the history of the solar system and have changed very little. These planets are much larger than the inner planets and are much more massive. In general, when planets or moons have thick atmospheres, they tend to experience a relatively narrow range of surface temperatures from day to night. Planets or moons with thin atmospheres often experience extremely large surface temperature ranges. For example, the Moon is much less massive than the Earth and has almost no atmosphere. Because it lacks a thick atmosphere to regulate its temperature, the Moon has a much wider surface temperature range than Earth. The same is true of Mercury, which has a very thin atmosphere and whose surface temperature varies by about 600 degrees Celsius from day to night. The universal law of gravitation. It states that every object with mass exerts a gravitational force on every other object with mass in the universe. The strength of this force is proportional to the masses of the objects and inversely proportional to the distance between them. So basically, if you look at this picture, it says every object in the universe attracts every other object with a force directed along the line of centers for the two objects that's proportional to the product of their masses and inversely proportional to the square of the separation between the two objects. Now, I'm not a math teacher, I'm a science teacher. However, we do use math in science. So if you look at the formula here, it's really not that bad because F with the G there is the gravitational force, and that's a standard number there, okay? M1 and M2, those are the masses of the two objects. So if you know the masses of the two objects, you've already got a couple numbers to plug into your equation. R is the separation between the two objects, and G is the universal gravitational constant. That doesn't change. That's why it's called a constant. Gravity is a force among all objects in the universe. Within our solar system, every object is attracted to every other object due to gravity. The closer objects are and the more mass they have, the stronger the attraction. Variations in gravitational forces among objects in the solar system cause variations in the object's orbital speeds. So as you can see from the picture, the force of gravity acts between all objects, and if mass increases, the force of gravity increases. If distance increases, the force of gravity decreases. The greater the total mass of two objects is, the greater the gravitational force between them is. For example, a meteoroid positioned halfway between two asteroids will be attracted more to the asteroid with the greater mass. Make sense? The difference in mass between two objects can also affect how gravity affects the object's motion. The motion of the less massive object is more affected by the force than is the motion of the more massive object. For example, the planet Jupiter is much more massive than its moons. This is why each of its moons orbit around the planet. The gravitational force between Jupiter and its moons does affect the motion of Jupiter, but only slightly. Another example of this is the orbits of all the planets around the Sun. The Sun is the most massive object in the solar system. This causes all the planet-moon systems, asteroids, meteoroids, and comets to orbit around the Sun. The Sun moves only slightly due to the gravitational force between it and the planets. Because of this, the Sun stays in the central part of the solar system, while the planets move in large orbits around it. The shorter the distance between two objects, the stronger the gravitational force between them. For example, because the Moon's orbit is elliptical, the gravitational force between the Earth and the Moon is stronger when the Moon is closer to the Earth. When the Moon is farther away in its orbit, the gravitational force between it and the Earth is weaker. Both distance and mass influence the gravitational force between two objects at the same time. Differences in distance have a greater effect on gravity than do differences in mass. For example, the gravitational force between the Earth and the Moon is stronger than the force between the Earth and the Sun. Even though the Sun has such a great mass, the shorter distance between the Earth and the Moon makes the force between the Earth and the Moon much stronger than the force between the Earth and the Sun. Let's look at the explanation on the next slide to understand what this means. So if you look here, you can see that the sun is 2 times 10 to the 27th metric tons. That's huge. However, with Earth and Moon being so close, you can see that the gravitational force between the Earth and the Moon is stronger. Gravity plays a vital role in the formation of the planets, stars, and solar systems. Stars, planets, galaxies, and galaxy clusters are all formed and held together by gravity. The gravitational force between a planet and the sun, along with the planet's continual forward motion, keeps the planet moving in an orbit around the sun. Each planet's orbit is shaped like an ellipse, which is similar to an oval. This gravitational force also determines the planet's orbital speed. The gravity between planets and the sun is stronger for planets closer to the sun than for planets farther away from the sun. The stronger the force, the faster the orbital speed. The planets, planetoids, asteroids, comets, and meteoroids of the solar system orbit the sun along oval-like paths. The force of gravity causes these objects to orbit the sun. The solar system is made up of the sun and all the objects that are gravitationally bound to it. This includes planets, planetoids, asteroids, comets, meteoroids, and moons. These objects orbit the sun along oval-like paths. The planets actually follow very nearly circular paths around the sun. The sun contains most of the mass in the solar system. Because of this, the sun exerts a strong gravitational force on other objects in the solar system. Over time, many objects, including the planets, have settled into orbits around the sun. The diagram below shows the order of the planets and the shape of their orbits around the sun. Each moon in the solar system orbits a planet and also orbits the sun. As a moon orbits its planet, the planet moves around the sun. So a moon orbits the sun at the same time as it orbits its planet. The sun is the only object in the solar system that is essentially stationary relative to the solar system as a whole. As the sun slowly orbits the center of the galaxy, the entire solar system comes along with it. So relative to the planets, moons, asteroids, and comets of the solar system, the sun does not move. Objects move in orbits around the sun or other objects due to their gravitational attraction and inertia. Without the sun's gravity, a planet's inertia would send it traveling in a straight line off into space, like shown in this picture below. Without a planet's inertia, the sun's gravity would pull the planet straight toward it, and the two would collide. These two factors combine to form an elliptical planetary orbit and determine the planet's orbital speed.